Welcome to the next video for Philosophy 10 Introduction to Logic at UCSD. This video I'm going to be talking about material that is currently in section 1.1 of the textbook, though I might flip 1.1 and 1.2 in the textbook because they can come in any order, it doesn't matter. But this is the part where we'll be talking about argument form. What is the form of an argument and how to determine an argument's form. So an argument is a set of statements, and as we said, right, what's an argument? It's a set of statements. One of those statements represents the conclusion of the argument. That's the new piece of information that is taken to follow from the other ones. The other statements represent the premise. They're called the premises, and they represent the initial information or the starting point. So that's what an argument is, as a representation of reasoning. An argument's logical form is going to be determined by the logical form of these statements, the premises and the conclusion. Now, a statement's logical form, okay, at least insofar as we're going to be talking about it in this class, this introductory course in logic, is going to be determined by the atomic statements that that statement has as components and the operators, if any, that combine those components. Okay, and this will make more sense in a minute. The first thing we need to do is distinguish between atomic and compound statements. Okay, first I'll give you some definitions and then we'll see some examples, and hopefully the examples will be clear. Now, a statement is something that makes a claim. It's typically expressed with a declarative sentence. Okay, it's not a question, it's not an imperative. It's something like the cat is on the mat. Okay. Now, an atomic statement is a statement that does not have parts that are themselves statements, whereas a compound statement is a statement that does have parts, maybe one or more than one, that are themselves statements. So let's see some examples of that. And we won't have to go too far to see some examples. So recall this argument. This is the rabbit argument. It has the same form as the pizza argument. I could have used that one as well. Notice, let's look at premise one. So premise one is a statement. It could be true or false. It's stating something as true or false. It says either the rabbit ran down the left trail or the rabbit ran down the right trail. Notice that this statement has parts, which are themselves statements, and I've underlined them. Okay. The rabbit ran down the left trail. That's a statement by itself. Now, you could use that on its own as a statement. And also this one, the rabbit ran down the right trail. That is also a statement that can be used by itself. Okay, no problem. So this is a compound statement. It has parts which are themselves statements. Okay, let's look at premise two. It also has a part which is itself a statement. The rabbit ran down the right trail. Okay, so two is compound. Now, it doesn't have two or more parts. It only has one part, and then this logical stuff here that we'll talk about in a minute. But that's enough to make it compound. The conclusion is atomic. It doesn't have any parts that are put together with statement operators like this, right? There's, the rabbit ran down the, is not a statement. Okay, so it's atomic. Now notice that this entire argument uses only two atomic statements. Okay, rabbit ran down the left trail, rabbit ran down the right trail. Premise one puts those two together into a compound statement in a certain way using either or. Premise two takes one of those statements but makes a compound statement with this it is false that language here. And then the conclusion just takes one of the atomic statements by itself, the same one that was up here. Okay? But the whole argument just uses those two statements. Now, this leads to the next point, which is that compound statements are built up from atomic statements with statement operators. So here's an example. This is an atomic or a compound statement, and it is built from parts. It has atomic statements that are sort of, you could think of them as glued together or built with this operator here, this either or. Here we have an atomic statement, and it's built into this larger compound statement with this thing going on here. It is false that. Okay. So we've seen two examples of statement operators, either or, and it is false that. Okay, and we've seen them in operation here. Okay. These operators, okay, are the things that build compound statements up from smaller statements. Okay. Now we're going to get 5 of those, 5 of these operators. Okay, and let's go through all 5. And in fact, these 5 operators compose pretty much everything that is in English, and is representative of how people think, the sort of logical operations of thought. In fact, you probably just negation, conjunct, the first 4 probably, biconditional, we probably wouldn't need. But in any case, here are the 5 that we're going to use in this class. The first is negation, and this is expressed in a number of ways in English. You could say it is false that, or sometimes you can just put an N apostrophe T on the verb of the statement that you're negating. Conjunction, usually it's expressed with and. Okay, roses are red and violets are blue, for example. Disjunction, or sometimes either or. Give me your wallet or I'll shoot, something like that. Conditional, if X then Y. If you bake the cookies too long, then the cookies will get burnt, for example. And then biconditional, if and only if. This is the one that we could probably do without if we had to. It's typically only used for the most part by computer science people or mathematicians or philosophers. But it does show up in English from time to time. For example, if you take the class pass-fail, pass-not pass, then the grading policy at UCSD states that you earn a pass if and only if you got a C- or better in the class. Okay, so let's see an example of how statement operators can be used to make compound statements from atomic statements. So here's a couple of atomic statements. John is at the party. There is pizza at the party. We could take the negation operator and apply it to the first one and get John isn't at the party. So this is a compound statement because it's this atomic statement plus this operator, the negation operator here. Here's conjunction that's putting both of these together. There's pizza at the party and John is at the party. Here we have a disjunction. Either John is at the party or there is pizza at the party. We could also use conditional. If there is pizza at the party, then John is at the party. Notice something interesting. These last 3 compound statements all had 2 components, 2 atomic statements, and the same 2 atomic statements were involved in all 3. Now, all 3 of them mean different things, and the difference in the meaning is because of the different operators. Conjunction, disjunction, conditional. These mean different things, okay? And they mean different things because of the different operators involved. That's crucial. Now, these operators have a cool property, which is that they are recursive. What does that mean? That means that they can take as input not only atomic statements, so they can do what I just said they do. They can build a compound statement out of atomic statements. They can do that. But in addition to that, they can take as inputs statements that are already compound to make even more complex compound statements. Now, that sounds kind of fancy, but you're already familiar with that from another field, which is arithmetic. So what I'm going to do is I'm going to do a little diversion here. I'm going to talk about arithmetic operators because you're all familiar with recursion of arithmetic operators. And then once I've reminded you of recursion in that context, it'll be easier for you to see what recursion is in the context of logic. So there are four big arithmetic operators, right? Addition, subtraction, multiplication, division. Okay? And the sort of atomic arithmetic expressions are numerals, like 1, 2, 3, 4, 5, whatever. Now we can use the arithmetic operators to put together these atomic expressions like 5 and 3 into compound expressions. 5 plus 3, 5 times 3, 5 minus 3, 5 divided by 3. Okay, so these operators are building up a more complicated expression from the simpler expressions, the atomic ones. Okay, so 5 is atomic, as an atomic statement in arithmetic, but 5 minus 3 is a compound statement. Okay, so you're all familiar with that. But the arithmetic operators are recursive in that they can operate on expressions that are themselves the product of an arithmetic operator. So for instance, not only can you do what I just showed you, you can use addition to put together two atomic expressions. I can use addition to put together two compound expressions. So each of the pieces that's put together by this operator was itself put together by an operator. Okay, this one was put together by multiplication. This one was put together by addition. And then we could use this whole thing and use the addition operator again to put this together with that and get an even more complicated expression. So this is what recursion is. It's where you can use the operators not only on the atomic expressions, but also on compound expressions to get more arbitrarily complicated expressions. Now the same thing is true in the case of logic. So here are some atomic statements, and we can put these together as I showed you a minute ago, right? We can take two of these. I can say, if you come to the party, then I'll steal your wallet. Okay, and that's putting together, you come to the party and I'll steal your wallet with an if-then operator. Okay, the conditional operator. But we can do something even more complicated. So get a load of this. If you come to the party and you don't pay me the $20 you owe me, then either I'll steal your wallet or I'll jack your ride. Okay, now this is a very complicated expression. Now, the interesting thing is that you all know exactly what this means. Even though if you try to analyze it, it's pretty sophisticated. It's telling you about a condition. Something is going to happen if something else happens, right? Namely, this is going to happen if that happens. But the condition is itself a conjunctive condition. It has two components to it. And the thing that will happen, the consequence, is itself complicated. It's a disjunction of two possibilities. Okay, so it's actually pretty sophisticated. Now what this is the conditional operator, if then, is putting together these two compound statements. It's saying if this thing in blue, then this stuff in yellow. Well, this thing in blue isn't an atomic sentence. It's actually compound. You come to the party and you don't pay me the $20 you owe me. Okay, so it's two statements put together with a conjunction operator. This is also compound. It's an either or. Either I'll steal your wallet or I'll jack your ride. And in fact, if we focus just on the this part, here are the two components. You come to the party, you don't pay me the $20 you owe me. Actually, the second one here, underlined in yellow, it's also compound because it's a negation operator. So there's actually 3 layers of recursion here. We've got the first layer, this was negated. The second layer, it was put together with conjunction to make this. And then the third layer is this was put together with this with an if-then. Okay? So this is just an example of recursion of these operators. And you can see now that you could make arbitrarily long statements this way. So what we want to do now is we want to translate from spoken language or natural language into a formal notation. Okay, and the way we're going to do that is first by translating the 5 operators into formal notation. And then once we've done that, we'll be able to translate compound statements into formal notation. And then once we can do the statements, we can do arguments that are made of statements. And in fact, that's trivial because an argument isn't anything other than a set of statements. So once we can do the statements, arguments are trivial. Okay. So step 1 is translating the different operators. And here's how it works. So let's do negation first. Negation shows up in English in a number of ways. So if I have an atomic statement like the cat is on the mat, here's some ways you can negate that in English. I could say the cat is not on the mat. The cat isn't on the mat. It is false that the cat is on the mat. It's not true that the cat is on the mat. Now these are all different in English, but they're all logically the same thing. They're all saying that my atomic statement is false. So they're logically all doing the same thing. Now, when we're translating into our formal notation, the first thing we do is identify all the atomic statements and assign to them a capital letter. So if I call this atomic statement C, okay, the cat is on the mat, it's atomic, and I'm just going to assign the letter C to that. That'll be the variable. Okay. Then all of these, cat is not on the mat, isn't on the mat, it's false that the cat is on the mat, we can translate into our notation as tilde C. So tilde is going to be our symbol for negation. And C is standing for our atomic statement here. So this means not C, the negation of C. Okay, so this would be how we would translate any of these 3 sentences here. So tilde is the symbol for negation. Next up, conjunction. Okay, so here's a couple of atomic statements. Roses are red, violets are blue. And here's a conjunction. And there's a number of ways in English to make conjunctions. Roses are red and violets are blue. Both roses are red and violets are blue. Roses are red, but violets are blue. You might think that's different, but it's really not. All of those are telling you that basically they're saying both of these atomic statements are true. If we assign, I'll say more about this later when we do the truth functions for conjunction. Why but is, well, I'll say it now. The reason it seems different, it is different. Logically, it's the same. The difference is that there's some additional non-logical import of the word but. Something like roses are red, but violets are blue, which kind of implies not only that they're both true, which is conjunction strictly speaking, but also that this one is a little surprising, let's say, given the truth of that one, or something like that. So there's some additional import of associated with the word but over and above the conjunctive, the fact that it's expressing conjunction. But it is expressing conjunction. Don't worry about that. Just remember but is a way of expressing conjunction in English. Okay, if we assign the letters R and V to these atomic statements, then we could translate all of these as R dot V. So dot is going to be our symbol for conjunction. Now, it's often going to be convenient for us to have names for components in a statement. So when we have a conjunction, we can refer to the components as conjuncts. So in this conjunction, the conjunction R and V, the first conjunct is R and the second conjunct is V. Okay, next up, disjunction. So here's two atomic statements. Dallas will win the Super Bowl, Buffalo will win the Super Bowl. And we can put these together with disjunction in English in a number of ways. I can say Dallas will win the Super Bowl or Buffalo will win the Super Bowl. I can just use or. I can use either or. Either Dallas will win the Super Bowl or Buffalo will win the Super Bowl. If we assign, let's say, D and B to these two atomic statements, then we could translate this or any of the other ones, either Dallas will win Super Bowl or Buffalo will win, as this, D wedge B. So we're going to use the wedge, it's like a lowercase v, as our symbol for disjunction. So you could read this as D or B. As was true of conjunctions, it's going to be often convenient for us to have names for the components of a disjunction. So we will call them disjuncts. So in this case, we have the disjunction D or B. The first disjunct is D, the second disjunct is B. Okay, next up is going to be conditional. Now, conditional is a little bit complicated. You're just going to have to bear with me on this. It's not my fault. I didn't invent English, but I'm just the messenger. Don't get mad at me. But English does things with conditionals that are a little bit complicated. But if you just sort of pay attention, it's not too bad. Okay, here's two atomic statements. You earn exactly 900 points. Let's call that N for 900. Okay, A will stand for you get some form of A. That would mean A minus A or A plus. Okay, so there's two atomic statements. Now I can put these statements together with a conditional. I can say, if you earn exactly 900 points, then you will get some form of A. Okay. The symbol we're going to use to symbolize a conditional is the horseshoe. So in this case, this would be N horseshoe A. Okay. So you earn exactly 900 points. That was N in red. You get some form of A in blue. That was A. So we have N horseshoe A. Now you might think, hey Rick, that looked easy. Well, it's actually more complicated than it looks. Okay. The question is the following. Or the point is the following. With conjunction and disjunction, we had two conjuncts, we had two disjuncts. One came first, one came second. It didn't matter. The first one that showed up in English, we just translated first into the formal notation, right? So for instance, with this, we had D or B. Why did we put D first? Well, we just put it because it showed up first here, right? It was before the or, and B came after the or. So we just put them in the same order, okay? With conditionals, things aren't so easy. It makes a difference, or let me put it this way. Well, I'll put it this way. The one following the if is going to be different from the one following the then, okay? So First off, this means we're going to give them different names. With conjunctions and disjunctions, we called both of the components the same thing. With a conjunction, they're both conjuncts. The one on the left is a conjunct, the one on the right is a conjunct. Same thing with disjunction. They were both disjuncts, okay, because it didn't matter. With conditional, it matters. One of the components of a conditional is going to be called the antecedent. The other component of a conditional is going to be the consequent. Okay, how do you know which is which? Well, if we have a conditional in English that's coded with an if-then statement, the one following if is going to be the antecedent, and the one following the then is going to be the consequent. Okay, so that's, I put the antecedent in red and the consequent in blue here. Okay, when we translate into the formal notation, the antecedent always goes on the left and the consequent always goes on the right. So that's why I put n on the left, is because n is the consequent. And I put a on the right because because n is the antecedent, and a is on the right because a is the consequent. Okay. Now what's tricky is that, well, first off, this doesn't apply to only if. So English, I'm going to talk about only if in a minute. There's a number of ways in English to express conditional. If and if then are a couple of ways. Only if is another way. What I just said right now doesn't apply to only if. There's a different way of doing it. But if it's an if, then, okay, the statement following if is the antecedent. Statement following the then is the consequent. Antecedent goes on the left, consequent goes on the right in the formal notation. Now the reason this is tricky is as follows. First off, you can omit the then, okay? So I could say, if you earn exactly 900 points, you will get some form of A. Of course, I could have put the then there. If you earn exactly 900 points, then you will earn some form of A. English lets you drop the then if it's obvious where it would be. Okay. In this case, it's a very similar rule. The statement following if is the antecedent. The other statement, which is, following where the then would be if there was a then there, is still going to be the consequent. Antecedent still goes on the left, consequent still goes on the right. Okay, so far so good. To summarize, the statement that follows the if is the antecedent. Statement following where the then would be if it was there is the consequent. Okay, if it's coded with if the then's actually there, then the statement following if is still the antecedent. Statement following the then is the consequent. So that's pretty straightforward. Here's the key though. The order in which they appear is irrelevant. All right, what do I mean by that? Look at this conditional. If you earn exactly 900 points, you will get some form of A. English lets you flip the order of those around, right? In English, you could say the same thing this way. You will get some form of A if you earn 900 points. Where all that happened here, I'll just color code these, is that in the first sentence, the if you earn 900 points was first and the get some form of A was last. And then in this sentence, English flipped them around. It says you can do that. You can put this first and this last if you want. Okay. But when it comes to translating into our formal notation, order does matter. Antecedents always go on the left. Consequents always go on the right. Okay. So what you need to do is when you're looking at the English version of a conditional, don't get caught up on which one shows up first. Don't say, oh, it's a conditional, this one was first, so I'm going to put it first here. No, because English might screw you up. English might put the antecedent second. Okay, how do you know it's the antecedent? Well, you know it's the antecedent because it's the thing following if. Okay, So here's another way of putting this. By the way, let me just give you a little graphic thing here. In the logical notation, antecedents are always on the left. In English, though, they always come first. In English, though, they might come first or second. Okay? English doesn't use order to code which one is the antecedent. How does English tell you then? It tells you with a code word. It uses the word if. The thing following if is the antecedent. The other statement is the consequent. That's how English tells you. It tells you with these code words, not with the order that they show up in. Okay? So, to put it another way, in English, which statement is the antecedent and which is the consequent is not coded by linear order, meaning it's not coded by which one is first and which one is second. Sometimes the antecedent is first, sometimes the antecedent is last in English. Okay, so you can't tell from the order that they're in English. How do you tell? You tell by looking for the code word, which in this case is if. Okay, the statement following if is going to be the antecedent. Statement following then is going to be the consequent, or the statement following where the then would be if it was there is the consequent. Okay, only if is a little bit different. Hold on a second on that. Okay, however, in our logical notation, the antecedent and consequent is what this should say. Sorry. The antecedent and consequent are coded by linear order. Okay, the antecedent is always on the left, consequent is always on the right. Okay, so let's summarize. Let's look at some examples. Jim will go to Hawaii if Jim wins lotto. Now you want to question on an exam, translate this into our formal notation. What do? Well, first thing you do is you find the atomic statements. Jim will go to Hawaii. Jim wins lotto. You assign to those atomic statements letters like H and L. I know it's going to be a conditional because it's if. It's not and or anything like that, or not. It's if. So that's telling me it's a conditional. So I'm going to use a horseshoe. Okay. What goes on the left of the horseshoe? It's always the antecedent. Okay, well, which one's the antecedent? Is it H or L? Well, let me look for my code word. Here's if. The thing following the if is Jim wins lotto. So L. So L is the antecedent. So L is going to go on the left. The other statement goes on the right. So it's going to be L horseshoe H. Okay. So here's my statement. Here's the atomic statements that are components. I've assigned these letters to the atomic statements. In translating from this, I know it's a conditional, so I know I've got a horseshoe. Statement following the if is the antecedent. So Jim wins lotto is the antecedent. So L is the antecedent. And in the formal notation, antecedent always goes on the left. So L's on the left. The other statement is the consequent and goes on the right. Now, what if instead of if, I had only if? Well, first off, those don't mean the same thing. Okay, you could kind of convince yourself of that if you wanted to. I'm not going to worry about it, but Jim will go to Hawaii if Jim wins lotto doesn't mean the same thing as Jim will go to Hawaii only if Jim wins lotto. All right. There's a different rule, which is this. It's different, but it's simple. If the conditional is coded with only if, then the statement following the only if is the consequent. Okay. So if we had Jim will go to Hawaii only if Jim wins lotto, I'm looking at this, I'm saying, oh, okay, only if, I know that's a conditional. What's the rule for only if? The rule for only if is the statement following only if is the consequent. So Jim wins lotto will be the consequent. That's L. So that is going to go on the right. Okay. Consequent on the right. Okay, so now let's just summarize this. Okay. For conditionals that use if, I'm going to get to only if in a minute, but first I'm summarizing conditionals that in English are coded with if. Okay. If it's by itself, okay, meaning it's not only if, it's just if. Sorry, I should have a not preceded by only. If is by itself, meaning it's not part of only if, then the statement following if is the antecedent. The other statement, which may or may not be preceded by a then, will be the consequent. Okay, so that's pretty easy. You don't care which one showed up first and which one showed up second in the English sentence. You care about which one's following the if. That is telling you which one is the consequent. On the other hand, if it's a situation where the conditional is being expressed with only if, here's the rule. The statement following only if is the consequent, and the other statement is the antecedent. Okay? So it's not too bad. All you need to do is when you're looking at a statement that's a conditional, ask yourself, okay, is it using if or is it using only if? If it's using if, the statement following if is the antecedent, the other one's the consequent. If it's only if, the statement following only if is the consequent, the other one's the antecedent. So when you summarize it, it's not too bad. You just have to remember two different rules. Okay? And then when you're translating into the notation, the antecedent's always on the left, consequent is always on the right. Okay, next operator, biconditional. This doesn't show up in English a whole lot. When it does, it's this way: something if and only if, or if with two F's. Could be something is necessary and sufficient for something else. That's another way of saying it. Here's an example. You will get a P in the class if and only if you earn a C- or better. That's actually official UCSD grading policy. You'll get if you're taking a PNP, pass not pass. A pass means C- or better. Okay. So there's a biconditional sentence. We want to translate that into formal notation. Step one, what are the atomic statements, and give each one of them a capital letter. So the atomic statements are, you will get a P. Okay, we'll call that P. And the next one is, you earn a C- or better. So we'll call that C. And once we've done that, we're going to translate the biconditional with this triple bar. P if and only if C. We don't have any special names for the components of a biconditional. So with conjunctions, we have two conjuncts. With a disjunction, we have two disjuncts. With a conditional, we have an antecedent and a consequent. With a biconditional, we don't have special names for the components. If we have to, we can just say the first component or the second component. Okay, well that's it for the first part of determining an argument's form. So we've translated the 5 statement operators. Next up, we're going to be doing compound statements. Okay, and then that'll close out the chapter.